Hello everyone, welcome back to another GeoStats lecture video. And in this lecture video, I want to talk about this idea of a lagged mean plot. Right, so in the previous video, we talked about lagged mean, what the equation looked like, how to calculate it. But where lagged means are really the most useful are in the way that we can plot them and the way that we can sort of interpret the plot. So let's go ahead and take a quick look at our data set over here. So again, this is the same thing we calculated in the previous data set. I went through and I finished the table up. I would have encouraged you at the end of the last video to pause and fill in the table. So hopefully you have all these values like I do. But what we're going to do is we're just going to quickly plot these data. So 33, 34, right, 35, 32.25, and so on and so forth. So what you're going to end up getting is a fully completed graph, and it should hopefully look something like this, where we have our points all plotted along in the plot here, and this black line here, I guess I should specify, right, this line right here, let's use a different color so it'll look better. Right, this line right here, right, this is a one-to-one line. So basically anything that falls along this line has the same y value as x value. Okay? So if you think about what the lagged mean plot is plotting, right, on the x-axis, right, this is our value. Right, this is our zi. Right, on the y-axis, we've plotted our lagged mean. Or our z bar I, right? So what is this one-to-one line actually telling us? Well, this one-to-one line means that the value at the polygon is the exact same as the lagged mean, which basically means if it was actually on this line, it would mean that all of the neighbors have the exact same value, right? That's what the mean is, right? In order for, if we had a value of 3 and we had a if we had a zi of 3 and a z bar I of 3, and we have 3 neighbors, that would mean that all 3 neighbors have to have a value of 3, right? I know that's kind of a dumb example, but again, if it falls on the line, that means that the neighbors have the same value as the polygon of interest. And the closer the point gets, right, the closer the point gets, right, the closer the point gets, I'm going to give myself a little bit more room here. Right, whoa. The closer the point gets, to the one-to-one line, the more similar the values of all of its neighbors are likely to be. Right, let me state that again because my handwriting got kind of bad. Right, the closer the point is to this one-to-one line, the more similar the value of all of its neighbors are likely to be. Because again, in order to be on the one-to-one line, that means that you have to have the same value as the average of all of your neighbors. Now, granted, right, you could have two very, very strong outliers cancel each other out. That's certainly a possibility. But generally speaking, right, the closer you get to this one-to-one line, the more similar values your neighbors have. And think about spatial autocorrelation, right? The more similar values your neighbors have, the more likely this data set is to display autocorrelation. Hopefully that sinks in. I'm going to repeat that one more time. Right? The closer the point is to the line, the more similar its values of all of its neighbors must be. The more points that are closer to the one-to-one line, right? The more total points are closer to the one-to-one line, the more likely the data set has autocorrelation. Right? Because again, the more points you have closer to this line, that means the more likely that you have these groups, right? Because again, this one-to-one line is when your polygon has the same value as the average of its neighbors. So the more points are closer and closer to this line, the more likely it is that you just have groups of polygons that have very similar values, which is sort of the definition, or a way of thinking about the definition of spatial autocorrelation. So hopefully that makes sense. Now, this was a fictitious example made up of 9 randomly generated numbers. So let's go ahead and look at an actual example that we would get from running code in R. Okay, so this is an actual data example here. This is actually the plot that we generate in the R coding tutorial for lagged means. And so what we have here, right, we still have this one-to-one line, right? This is still the one-to-one line right here. But we can see here that the data does not nearly as closely follow this one-to-one line, right? Not like our example did, right? Just sort of think about how far away so many of these points are from the one-to-one line relative to our little example here. So this data set is less likely to have autocorrelation, or if it does have autocorrelation, it's not likely as severe, right? Because the more points that get closer to this one-to-one line, the more likely you are to have autocorrelation, and the more severe that autocorrelation is likely to be. So hopefully that makes sense. Again, hopefully you understand how this plot's made, what the axes are, what this one-to-one line represents, and just a general sense of how to look at this and get some meaning out of it. And as always, please reach out. Thank you.